Section 8.6 deals with oxymercuration-demercuration, and if you remember that Markovnikov hydration, acid-catalyzed hydration, has some limited applications in that we can get rearrangements, so carbocation rearrangements. And the problem with carbocation rearrangements is that we end up getting a mixture of products. So what's great about oxymercuration-demercuration is that even though you have to use mercury, which is toxic, you end up doing a Markovnikov addition of water. So we add our hydrogen and our hydroxyl to produce an alcohol, but the beauty is that no rearrangements can occur. There's no easy way around memorizing the reagents. You just have to sit down and learn them. So step number 1 is we use mercuric acetate and water, and in step 2 we use sodium borohydride. So you have to remember those two reagents, or those two sets of reagents, and you also have to put the numbers, because if you were to combine mercuric acetate and water with sodium borohydride, you would not get this reaction. You would just get a mess of products. So you have to remember to write step 1 is mercuric acetate and water, and step 2 is sodium borohydride. We get addition of water, and the beauty is no rearrangement. Something you could do to practice is you could practice drawing the mechanism for what would happen if I was to treat that with hydronium. So we'd end up actually proceeding through a carbocation intermediate that would undergo a rearrangement, and I would end up with this alcohol. So you could practice drawing the mechanism for that reaction. This slide shows a little bit about the mechanism of oxymercuration-demercuration. You'll never be asked to draw the mechanism of oxymercuration-demercuration, but it's a good idea to understand how it works. The more you understand organic chemistry, the easier it is. So it says here that when the pi bond attacks the mercury cation, a stabilized cation is formed, and so it will not rearrange like carbocations do. So if we compare the two, if we compare when a pi bond is protonated, I end up with a carbocation, and carbocations can rearrange. It says here that when a pi bond attacks the mercuric cation, and this species here is the mercuric cation, that I end up with a mercurinium ion. The mercurinium ion is more adequately described as a hybrid of two resonance structures. So a mercurinium ion has some of the character of a carbocation, but it also has some of the character of a bridged three-membered ring. This dual character can be illustrated on the following slide. So you can see here that the more substituted carbon atom bears a partial positive charge, the delta plus, right here, rather than a full positive charge. As a result of this, the intermediate will not readily undergo carbocation rearrangements, but it's still subject to attack by a nucleophile, as is shown here. Notice that the attack takes place at the more substituted carbon of the two, ultimately leading to Markovnikov addition. After attack of the nucleophile, the mercury can be removed through a process called demercuration. The way we do the demercuration is using sodium borohydride, and it proceeds via a radical process. The net result is the addition of hydrogen and a nucleophile across the alkene. So the two reaction sequence provides the same product as acid-catalyzed hydration, but you don't get any carbocation rearrangements. So if I take this alkene and I treat it with hydronium, I end up with a mixture of products. And the reason why is because the mechanism proceeds through a carbocation intermediate. Because of the different mechanism, when I do oxymercuration-demercuration, I get no rearrangements. So it says here that a 1,2 methide shift would occur if you had used sulfuric acid and water in this case. So oxymercuration-demercuration is a really beautiful way of adding water across a double bond and avoiding carbocation rearrangements. So you're always going to have to be on the lookout for an alkene that can undergo carbocation rearrangements. If you want to avoid them, then you're going to have to employ the conditions of oxymercuration-demercuration, a very useful reaction.